Hello, I'm Zachary Mead, and today I will be presenting on an integrated brain-machine interface platform with thousands of channels. So a little introduction. So this study is based around Neurolink that has built an effective brain-to-machine interface, the acronym BMI, which holds a promise for the restoration of sensor and motor function for the treatment of neurological disorders. And I want to just note that this still has not been accepted for clinical use. But Neuralink has built an array of small flexible electrodes called threads with as many as just over 3,000 electrodes per day that array across 96 threads. They also built a neurosurgical robot capable of inserting 6 threads, about 192 electrodes per minute. Each thread can be individually inserted into the brain with a micron precision for the avoidance of surface vascular and targeting of specific brain regions. This is just basically to avoid injury and to get it more precise, to make sure that area of the brain is most precise where you're implanting it. An electrode array is packaged into a small implantable device that contains a custom chip for low power of onboard amplification and digitalization. So the brain-machine interface is unprecedented in the packing density and the scalability as it is clinically relevant in its package size. So the brain-machine interface has the potential to help many people with a wide range of clinical disorders, many based around neuroscience, ranging from multiple sclerosis, spinal injury, Parkinson's, etc. For example, researchers have demonstrated that human and neuroprosthetic control across computer cursors, robotic limbs, and speech synthesizers by using no more than 256 electrodes, which is a small amount of what they could do. So how this works. So in simple, the tiny electrodes, the threads, penetrate the outer face surface of the brain, detecting the electrical impulse from the nerve cells that shows how the brain is at work. In line with Neuralink's long-term plans, the threads are the design and communicate back to the computer and generates their own signal. So Elon-Musk is the leader of Neuralink, and his quote, I think it really describes it really well. It's like a Fitbit in your skull with tiny wires. It communicates with your brain cells through about 1,024 thin electrodes that penetrate the outer layer of the brain, and a Bluetooth link outside to an outside computing device. The company is looking for more radio technologies, which can drastically increase the number of data links, how fast the data can be uploaded, and the amount of things you can view at a time. So a little bit more into this. This is kind of right now solely a research platform that's been used in rodents and serves as a prototype for future human clinical applications. This is important. The performance assessments are crucial for the development of signal processing and decoding all the algorithms. Clinical devices that derive from this platform will usually be implantable, which researchers requires hermetic packaging and have a onboard signal compression, reducing power consumption, and wireless power transmission and data telemetry through the skin without precautionary leads. So basically, it won't have wires hanging out and a big battery pack. This brain machine interface system has several advantages to other previous approaches, the two being the size and the composition of the thin film probes, which are better matched for the material and properties of the brain tissue that have commonly used silicone probes that may exhibit enhanced biocapability. So this has the ability to choose where the probes are inserted, including into the subcortical structures, which allows them to create a very custom arrays of geometric for targeting specific brain regions while avoiding vasculature. Neuralink's approach to the brain-machine interface is highly extensible and is very scalable, which is another big claim to fame from it. They showed this stimulus broad brain recording over 3,000 inserted electrodes in a freely moving rat, which was incredible because earlier I mentioned they did the arm movement with just over 250. So hopefully in a larger brain, example being a human, multiple devices within this architecture could be readily implanted, and therefore the interface can have many more electrodes without extensive re-engineering. The hope is to expedite the development of surgical robots that could allow Neurolink to accomplish this without dramatically increasing surgical time, so surgery can be done at warp speed almost. Although significant technological challenges must be addressed before this device is suitable for clinical application, it is plausible to imagine a patient with a spinal cord injury could dexterously control a digital mouse or a keyboard, which would be huge. Neuralink is the biggest benefit to rapidly improving spinal stimulus techniques in the future, and this hope is this is kind of hopeful for people who have spinal cord injury that they could conceivably restore motor function one day. Future application of Neuralink is basically endless. It can be used for many future applications regarding where studying disease, understanding how the brain works, brain mapping, and etc. Future application is endless. Thank you very much for listening to my presentation today.